Hello, my curious friend, and a very warm welcome to Deep Field channel. Tonight we are going to journey through something that exists right above your head, deep beneath your feet, and in every direction you can possibly imagine all at once. The invisible skeleton of the universe, that cosmic web sustaining the existence of everything that ever was or ever will be. And I promise to try not to make this topic so utterly captivating that it keeps your eyes wide open when they should be slowly drifting shut. But before we embark on this voyage, I would love to know in the comments which little corner of the world you are tuning in from tonight. And if you are feeling too lazy to type, just leave a simple hello. That tiny gesture tells YouTube that this is a welcoming space and helps us bring more weary minds to rest with us. If you enjoy these nocturnal scientific journeys, please leave a like and subscribe to the channel. And to those who are already part of this beautiful community, my most sincere thanks. Now, wherever you might be, find a truly comfortable position. If sleep arrives before we reach the end, accept the invitation without any guilt. Let us begin. There is something you have never seen, yet it dictated where you were born. I am not talking about destiny or mysticism. I am referring to a physical, real, measurable structure that began taking shape less than 1 billion years after the birth of the universe and has never stopped growing, branching out, and deepening ever since. This structure is the cosmic web, and it is likely the most vast yet simultaneously the most delicate thing science has ever uncovered. Think for a moment about the last time you took an early morning walk and stumbled upon a spider web draped in dew. Every single droplet of water clinging to a delicate thread caught the sunlight in a unique way, making the entire web look like a map of bright dots linked by nearly invisible lines. Now expand that image. Expand it until your imagination gives out. Picture each of those droplets as an entire galaxy, harboring hundreds of billions of stars within. Envision the connecting threads spanning tens of millions of light years in width. Imagine the whole web stretching across a distance that light, traveling at the absolute fastest speed in the universe, would take over 90 billion years to cross. That is the cosmic web. And it is no mere metaphor, it is the actual architecture of the cosmos. When most folks picture the universe, they envision something akin to an ocean of stars, a somewhat even scattering of matter in every direction. It is a lovely image, but fundamentally flawed. The universe is not uniform. It is profoundly textured, riddled with grooves and voids, with heavily populated zones and absolutely barren expanses. This unevenness is no accident. It is the most accurate signature of how the cosmos operates, the most fundamental mechanics in existence written on an astronomical scale. The very first thing that catches almost everyone off guard when learning about the cosmic web is that the vast majority of the universe is empty. Not just partially empty, not just sparsely populated, empty in a way that defies human intuition. There are regions of the cosmos known as cosmic voids where practically zero galaxies exist. These voids span dimensions, ranging from tens to hundreds of millions of light years across. To put that into perspective, the Milky Way, the galaxy you call home, is roughly 100,000 light years in diameter. A typical void is hundreds of times larger than that, and inside it there is almost nothing. Just darkness, expansion, and the unseen presence of something we will get to know better a bit later. All the matter you are familiar with, all the matter that builds stars, planets, dust, gas, and yourself is compressed along the borders of these voids. These borders form filaments, which act much like the threads of a spider web. And where these filaments intersect, you find what astronomers call nodes or galaxy superclusters, regions where hundreds or even thousands of galaxies gather in a slow, intricate gravitational dance. Our own local group of galaxies, which includes the Milky Way and Andromeda, sits in a relatively calm area, close to but not precisely inside one of these giant nodes. Now here comes the first major twist. The detail that usually makes people snap their eyes wide open right when they were trying to close them. This entire colossal structure, this whole web that dictates where galaxies do and do not exist, was forged primarily by something that emits no light, reflects no light, and does not interact with light in any capacity. Ordinary matter, the stuff that makes up you and everything you can touch, accounts for merely about 5% of the universe's total content. The rest, over 94%, consists of dark matter and dark energy, two phenomena we cannot see directly, cannot touch, and do not fully understand, yet whose gravitational and expansive influence has sculpted every single detail of the structure we are exploring tonight. This means that when you gaze at a photograph of a galaxy and marvel at its brilliant stars and spiral arms, you are looking at the smallest fraction of the story. The main chapter is invisible all around it, a massive sphere of dark matter enveloping the galaxy, holding it together and preventing it from being torn apart by the universe's expansion. And when you look at the cosmic web as a whole, the filaments linking the galaxies are predominantly made of this very same dark matter, with galaxies nestled inside them like ornaments on a Christmas string you cannot see. There is a popular myth worth carefully dismantling. Many folks assume that astronomy is a science of absolute certainties, that we simply look at the sky, take measurements, and know the answers. The cosmic web challenges this notion beautifully. We discovered it before we truly understood it. The earliest hints that galaxies were not scattered randomly came from three-dimensional surveys conducted in the late 20th century, when astronomers began mapping not just the position of galaxies in the sky, but also their distance, and thus their true location in three-dimensional space. What they uncovered was deeply unsettling. Galaxies formed sheets, filaments, and clusters, and between them lay immense volumes of emptiness. They seemed to have followed a blueprint, yet no human architect had drawn it. The discovery was perplexing enough that many astronomers hesitated to accept what the data was showing. The human mind is not well equipped to visualize structures spanning hundreds of millions of light years. Our direct experience is limited to landscapes we can cross in hours or days. Even the concept of a star a few light years away pushes the limits of our intuitive visualization. So when the data indicated that a neighboring galaxy was 2 million light years away and that an organized structure stretched 5,000 times further than that, the instinct was to doubt the method, not the universe. But the universe repeatedly validated itself. Every new survey, every new telescope, every novel mapping technique revealed the exact same picture, the web. And it does not merely exist, it possesses an internal coherence, a logic that can be replicated in computer simulations with astonishing accuracy. When cosmologists use the equations of physics to simulate the universe's evolution from the Big Bang to the present, allowing gravity and expansion to act upon the initial distribution of matter, the outcome is a web that looks remarkably like what we observe. This stands as one of the most powerful confirmations that we grasp at least the general principles of how the cosmos operates. The sheer scale of the cosmic web demands that we pause for a moment to contemplate what the word scale truly means in this context. A light year is the distance light travels in 1 year, moving at 300,000 kilometers per second. That is already a distance that shatters any everyday human frame of reference. The closest star to the Sun is just over 4 light years away. Our galaxy spans 100,000 light years in diameter. The local group of galaxies we belong to stretches about 10 million light years across. The Laniakea supercluster, the larger structure we inhabit, is 500 million light years wide, and the cosmic web extends for tens of billions of light years in every direction, right up to the edge of the observable universe. Within this framework, the filaments act like rivers of dark matter and galaxies. They can stretch for hundreds of millions of light years in length and span tens of millions of light years in width. The nodes where these filaments converge are the superclusters, zones of extreme density where gravity has concentrated matter over billions of years, and the voids between the filaments are practically desolate, though not entirely empty. Solitary galaxies wander through them, galaxies that were somehow ejected from their original structures or never belonged to any in the first place. The composition of these filaments deserves special attention. Beyond the visible galaxies, the filaments harbor massive quantities of hot gas, particularly ionized hydrogen, at temperatures ranging from hundreds of thousands to millions of degrees. This gas is known as the warm-hot intergalactic medium, and for a long time it was one of cosmology's most baffling puzzles because models predicted its existence, but available instruments could not detect it directly. In recent years, new X-ray observations and specific radio wavelengths have begun to uncover this gaseous component, confirming that filaments are not just dark matter tracks with galaxies wedged into them, but rich, complex structures with their own dynamics. There is another trait of the cosmic web that is often underestimated. It is dynamic. It is not a static framework that was built once and left unchanged. It continues to evolve. Filaments keep funneling matter toward the nodes. Voids keep expanding. Superclusters keep trying to collapse under their own gravity, even as the universe's expansion pulls everything away from everything else. It is a perpetual tug-of-war between the gravity that seeks to unite and the expansion that seeks to divide, and the cosmic web is the visual record of this tension at every stage of its evolution. Now consider something simple that you know well. Think about how water flows across a landscape. Water does not pick its path at random. It follows the lowest points, the valleys, the grooves that gravity has carved into the terrain. Over time, rivers carve channels that grow deeper because more water flows through them, which in turn draws even more water. Mountains appear taller relative to the valleys, not because they are growing, but because the valleys are deepening. There is a positive feedback logic where the existing structure draws more matter to itself, sharpening the contrasts. The cosmic web operates in a surprisingly similar fashion. The minor variations in matter density that existed shortly after the Big Bang created slightly denser regions and slightly less dense regions. Gravity handled the rest. The denser zones pulled matter from neighboring areas, which became even less dense, causing the dense zones to become even denser. This process of gravitational amplification, which cosmologists refer to as Jeans instability or perturbation growth, transformed minuscule fluctuations into colossal structures over billions of years. The seed of these fluctuations is a fascinating story in itself. The tiny irregularities that gave rise to the entire cosmic web were not generated by any macroscopic process. They were born from quantum fluctuations, random variations in the energy field that filled the universe in the very first moments after the Big Bang, during a period of hyper-accelerated expansion known as cosmic inflation. Fluctuations that existed on a subatomic scale were stretched by the expansion to cosmic dimensions, becoming the seeds of all the structure we see today. This means the cosmic web, with its filaments spanning hundreds of millions of light years, is the gravitational amplification of quantum events. The largest and the smallest are linked in a way that makes the mind pause for a moment. Dark matter played an absolutely crucial role in this process, and it is vital to understand why, even without knowing exactly what dark matter is. Ordinary matter, the atoms that build stars, planets, and you, interacts with light. This means that during the first 380,000 years of the universe, When everything was so hot and dense that light was trapped, radiation pressure prevented ordinary matter from collapsing under its own gravity. It just bounced around like a compressed fluid. Dark matter, because it does not interact with light, did not suffer this pressure. It could begin collapsing and forming structures much earlier. When ordinary matter was finally freed from radiation pressure, it found a sort of dark matter skeleton already in place and simply fell into it. The dark matter web came first, and the web of visible galaxies is merely the luminous filling of a pre-existing invisible framework. This makes the cosmic web doubly invisible. Its primary architecture is constructed from a substance we cannot see. And even the part we can see, the galaxies with their bright stars, represents only a minuscule fraction of the total matter contained within the filaments. We are observers of the decoration, trying to deduce the building structure by looking at the placement of the pictures on the walls. There is yet another scale of structure above all this that deserves a mention, if only so you can feel the full weight of what we are contemplating. When we map the cosmic web on a large enough scale, we begin to see that the superclusters themselves, the giant nodes where filaments cross, are organized into even larger formations. There are sheets of galaxies known as great walls that span billions of light years in length, and there are ongoing debates among cosmologists about whether there is any structure above this, or if at a certain scale the universe finally begins to look uniform, as standard cosmological models predict. This question of large-scale uniformity is not trivial. If the universe is infinite or vastly larger than our observable region, and if the laws of physics are the same everywhere, then it is expected that on a sufficiently large scale, the universe should look identical in all directions, without any privileged structures. This is known as the cosmological principle. The cosmic web, as vast as it is, exists within a scale where irregularities still dominate. On scales of billions of light years, density fluctuations begin to smooth out, and the universe starts to approach the predicted uniformity. But we reach this state gradually, not abruptly, and the exact point where the web loses its organization remains an active field of investigation. You might be wondering right now, in a vague and perhaps sleepy way, how something as cold as gravity, this force that only pulls and never pushes, could have created such a complex structure so full of motion. How can a passive force have organized the initial chaos into filaments, nodes, and voids with such precision? How do billions of galaxies know exactly where to be? And this is where the story begins to get even deeper, because the answer involves not just the gravity that pulls, but also something that pushes, something we cannot fully name, something that is present in every cubic centimeter of empty space, and that governs the fate of everything that exists, including the very web we have just begun to understand. Where does the energy come from that animates this system, that makes the web move, that inflates the voids, that determines whether the filaments will keep growing or slowly unravel over the next few billion years? That is the question that will float with you as sleep approaches. Let it hover. Let it rest gently as you breathe. There is a force you have never felt directly, yet it determined where you were born, in which galaxy, in which spiral arm, in which tiny corner of a cosmic filament stretching for hundreds of millions of light years. This force has no scent, no color, emits no sound. It does not choose, it does not hesitate, it simply pulls, always pulls, and never stops pulling. And the strange thing is that a force so simple in its nature, so monotonous in its behavior, so devoid of apparent sophistication, was capable of sculpting the most complex structure in the observable universe. The cosmic web was not drawn, it was pulled. Think about how a spider web is formed. The arachnid does not start with an architectural blueprint. It follows simple rules, one line after another, tension after tension, and the result is a geometry that seems calculated with mathematical precision. Nature does this repeatedly, on scales ranging from the microscopic to the astronomical. It establishes a law, lets that law act over time, and what emerges is something no architect could have designed with intention. The cosmic web is the result of this same unconscious wisdom, but operating on scales of time and space that the human mind can only grasp partially, like fingers trying to hold onto mist. The force behind all of this is gravity, but the gravity that created the cosmic web is not exactly the gravity you experience in daily life. It is not just the force that keeps you in your chair or made the apple fall. It is gravity accumulated over billions of years, acting on quantities of matter so vast that writing out the number would require a string of digits long enough to fill several pages. It is gravity operating in a universe that was, at the beginning, almost completely uniform, almost perfectly smooth, with nearly identical densities at every point. Almost. That single word holds the entire universe within it. The primordial universe was like a perfectly calm ocean, but with almost imperceptible ripples on its surface. These ripples were so subtle that if you looked at them, you would need instruments of extreme precision to notice any difference from one point to another. But gravity is patient. Gravity is in no rush. It felt these tiny density differences and went to work. The slightly denser spots began to attract a bit more matter than the slightly less dense spots, and this minimal difference, amplified over hundreds of millions of years, generated everything you can see when you look up at the night sky. There is a law governing this process that was understood long before we knew the cosmic web existed. Isaac Newton described it with an elegance that still seems almost miraculous in its simplicity today. Two bodies attract each other with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This means that the greater the mass, the stronger the attraction. And the closer the bodies, the much more intense the force between them, because the distance is squared in the calculation. If you halve the distance, the force does not just double, it quadruples. If you reduce the distance to a third, the force multiplies by 9. This non-linear progression is fundamental to understanding why the cosmic web has the shape it does. Imagine you are in a room with hundreds of styrofoam balls floating in the air, distributed almost uniformly, but with a few minor variations. The balls that are slightly closer to one another begin to attract each other a bit more. This extra attraction pulls them even closer, which intensifies the attraction between them, which pulls them even closer still in a continuously self-feeding cycle. Meanwhile, the regions that became a bit emptier grow progressively emptier because the matter at their edges is gradually stolen by the denser regions around them. What starts as an almost imperceptible difference transforms, given enough time, into an absolute contrast between full regions and practically empty ones. This process has a technical name. Cosmologists call it gravitational instability, and it was the physicist James Jeans who formalized it mathematically in the early 20th century. Jeans was working on the problem of how gas clouds collapse to form stars, but the mechanism he described is the exact same one operating on cosmological scales. There is a critical scale, known as the Jeans length, above which a gas cloud cannot resist its own gravity and inevitably collapses. Below this scale, the gas's internal pressure can resist. The primordial universe was filled with perturbations on various scales, and those that exceeded the relevant Jeans length began to collapse, while the smaller ones oscillated like sound waves trapped in a fluid. But Newton's law, as powerful as it is, does not tell the complete story of the cosmic web. Newton described gravity as a force that acts instantaneously across space, connecting two bodies without anything mediating that connection. He himself found this disturbing. In his letters, he admitted that the idea of a force acting at a distance without any transmission medium was so absurd that he did not believe anyone capable of thought could accept it. He was right to be uncomfortable. A deeper description of gravity would come more than 200 years later, and it would completely change how we understand the universe on a grand scale. Albert Einstein spent 10 years working on a problem no one else recognized as urgent. Newton had perfectly described what gravity did. Why question it? But Einstein was bothered by a fundamental inconsistency. The theory of special relativity, which he had proposed in 1905, established that nothing could travel faster than light. But Newtonian gravity was instantaneous. If the sun suddenly vanished, the Earth should feel the absence of its pull immediately, before the sun's light even stopped arriving. This violated everything Einstein had discovered. Something was wrong. What Einstein proposed after a decade of effort that he himself described as the most intense and revealing period of his intellectual life was that gravity is not a force in the traditional sense. Gravity is the curvature of space and time itself. Matter and energy do not just exist in space, they bend it, and other objects follow the straightest possible paths through this curved space. What appears to be an attraction between two bodies is actually both bodies following the geodesics, the natural paths, of a geometry they themselves helped shape. The Earth is not pulled toward the sun, it simply follows the straightest possible path in the curved space the sun created around it, and that straightest path is an orbit. This perspective has profound implications for the cosmic web. It means that the universe as a whole has a geometry, a shape, and that this shape changes over time as the matter within it moves and reorganizes. Einstein's equations do not just describe how individual objects move in curved space. They describe how space itself behaves, how it can expand, contract, twist, and pulse. And it was right here in the mathematical solutions to Einstein's field equations that a possibility no one had seriously considered first appeared. Alexander Friedmann, a Russian mathematician working in St. Petersburg in the early 1920s, found solutions to Einstein's equations that described an expanding universe. Einstein, upon seeing Friedmann's work, initially thought there was a mathematical error. Later, upon checking the calculations more carefully, he acknowledged they were mathematically correct, but still resisted the physical interpretation. An expanding universe seemed counterintuitive, almost unthinkable. The entire worldview of the time assumed a static, eternal cosmos without beginning or end. The idea that space itself was growing was too disturbing to be easily accepted, but observation does not care what scientists prefer. Edwin Hubble, working at Mount Wilson in California, was cataloging galaxies with a patience bordering on asceticism. Night after night, he measured the brightness of stars in distant galaxies and recorded what we call the redshift of the light arriving from those galaxies. Light from a receding source has its wavelength stretched, shifted toward the red end of the spectrum. And what Hubble discovered was that practically all galaxies beyond our immediate neighborhood were moving away from us, and the more distant ones were receding faster than the closer ones. The universe was expanding. This discovery, confirmed in 1929, not only validated Einstein's equations, it revealed something even more unsettling. If the universe is expanding now, then in the past it was smaller. And if you keep rewinding time, you reach a moment when everything was compressed into a state of such extreme density and temperature that the laws of physics as we know them cease to apply. The universe had a beginning. This beginning left an echo, a background radiation that still permeates the entire cosmos, and imprinted in this radiation are the seeds of everything that would come later, including the seeds of the cosmic web. The cosmic microwave background radiation is the oldest map of the universe. It was emitted about 380,000 years after the beginning of everything, when the universe cooled enough for electrons to combine with protons and the cosmos became transparent to light for the first time. This radiation reaches us from all directions with an extraordinarily uniform temperature, but not perfectly uniform. There are temperature fluctuations on the order of 1 part in 100,000, tiny variations that represent the small density differences that existed in that primordial universe. And when cosmologists mapped these fluctuations with increasing precision, especially with the COBE, WMAP, and Planck satellites over the last few decades, they found exactly the kind of pattern needed to produce the cosmic web we observe today. Gravity took these tiny fluctuations and amplified them over billions of years. But here enters the second character of this story, the one promised at the end of the previous section, the force that pushes. And to understand this force, you first need to understand that Einstein committed what he called the biggest mistake of his life, and that this mistake ended up revealing a brilliant prediction of something he himself could not imagine. When Einstein applied his equations to the universe as a whole, they predicted that the cosmos should be in motion, expanding or contracting. To preserve the view of a static universe, he introduced an additional term into his equations, a cosmological constant, a sort of repulsive force distributed uniformly throughout space that would balance the gravitational attraction of matter and keep the universe still. When Hubble discovered the expansion, Einstein removed the cosmological constant from his equations, regretting that he had tampered with the original beauty of his theory. But he removed it too soon. In 1998, two teams of astronomers were measuring the expansion rate of the universe using a specific type of stellar explosion, Type 1a supernova A, which have such a well-determined intrinsic luminosity that they act as standard candles in the cosmos. Knowing how bright such a supernova should be, you can accurately calculate its distance from how faint it appears in the sky. The two teams, led respectively by Saul Perlmutter and the duo Brian Schmidt and Adam Rees, expected to find that the universe's expansion was slowing down, braked by the gravity of all existing matter. What they found was the opposite. The expansion was accelerating. Something was pushing the universe outward with a growing force. This something was named dark energy, a name that honestly admits our ignorance about its nature. Dark not because it is sinister or threatening, but because it emits no light, absorbs no light, and does not interact with matter in any known way except through its gravitational effects, and even those effects are opposite to those of ordinary matter. Instead of attracting, dark energy repels, making space expand faster than it would just from the inertia of the initial impulse. Measurements indicate that dark energy makes up about 68 parts per 100 of everything in the universe. Dark matter, which we will discuss shortly with the attention it deserves, accounts for about 27 parts per 100. All ordinary matter, stars, planets, gas, dust, you, me, everything we can see and touch and measure directly, represents only 5 parts per 100 of the universe's total content. This means that the cosmic web, this invisible skeleton organizing all visible matter, is immersed in an ocean of substances we cannot see, cannot detect directly, and do not understand in their essence. Dark energy permeates every cubic centimeter of empty space. It does not dilute as space expands, unlike matter and radiation. It is a property of space itself, a tension that exists in the vacuum and that increases in total magnitude as the volume of the universe grows. The more the universe expands, the more space there is, the more dark energy there is, the stronger the acceleration of expansion becomes. It is a process that feeds on itself. And here is the fundamental imbalance that makes the cosmic web work the way it does. There is a tension between two forces of completely different natures: gravity, which is attractive, which acts more intensely on small scales and tends to clump matter into increasingly dense structures, filaments, nodes, clusters, and dark energy, which is repulsive, which acts on large scales, which tends to separate large structures from one another and inflate the voids between them. The cosmic web is the result of the continuous interaction between these two forces on different scales. On scales smaller than a few 100 million light-years, gravity dominates. Matter manages to clump together, form filaments, condense galaxies. On larger scales, dark energy begins to prevail, and superstructures become increasingly isolated from each other as the space between them expands faster than gravity can fill it. Astronomers calculate that there is a maximum scale above which no gravitationally bound structure can exist in the current universe. Above this scale, accelerated expansion separates everything irremediably. This implies that the cosmic web is not a static structure, it is constantly evolving. The filaments that exist today are denser than those that existed 5 billion years ago. The nodes where filaments intersect, those places called galaxy clusters, continue to grow as they accumulate more matter over time. The voids, the huge bubbles of nearly empty space that occupy most of the universe's volume, continue to expand, becoming progressively more isolated from the matter that exists at their edges. And at some point in the distant future, if dark energy continues to behave as it has shown, the thinnest filaments will begin to dissolve, unable to maintain their cohesion against accelerated expansion. But that future is billions of years away, and what matters now is understanding how this tension between attraction and repulsion created the specific geometry we observe. Think of a rubber sheet that you stretch in all directions simultaneously while pouring a thin layer of wet sand over it. The sand, under the effect of the moving surface and its own interactions, will organize into patterns. Where the rubber bends slightly, the sand accumulates. Where the rubber stretches more smoothly, the sand disperses. The result is a network of higher density lines separated by lower density regions. Now imagine that this rubber sheet has 3 dimensions instead of 2, that the sand is not just sand but dark matter and primordial gas, and that the process happens over billions of years instead of seconds. What you have is a rough but instructively useful approximation of the process that formed the cosmic web. Dark matter was the first ingredient to organize. Because it does not interact with light and the radiation pressure of the young universe, it could begin to clump much earlier than ordinary matter. It formed a sort of invisible scaffolding, a preliminary structure of slightly denser regions and slightly less dense regions. And it was onto this scaffolding that ordinary matter, the hydrogen and helium gas of the primordial universe, gradually settled as the universe cooled. Where dark matter had created a filament of high density, gas flowed there. Where dark matter had left a void, gas was drained toward the denser edges. It was Fritz Zwicky who first suspected there was a significant amount of invisible matter in the universe. In the 1930s and 40s, he was studying the Coma cluster, a group of galaxies hundreds of millions of light years away, and realized that the galaxies were moving too fast to be held together solely by the gravitational attraction of visible matter. There was more gravitational pull than visible matter could explain. Zwicky was largely ignored for decades. It was an observation too disturbing to be accepted without more evidence. Vera Rubin changed that. Working in the 1960s and 70s, she studied the rotation of spiral galaxies with a precision no one had achieved before. Stars at the edges of galaxies, much further from the center than inner stars, should be moving more slowly, just as the outer planets of the solar system orbit the Sun more slowly than the inner planets. This is what Newtonian physics predicts when most of the mass is concentrated in the center. But what Rubin found was that stars at the edges of galaxies moved almost as fast as stars near the center, as if there were an invisible mass distributed in a huge sphere around each galaxy, providing extra gravity in the outer regions. This invisible mass is dark matter, and it forms a spherical halo around each galaxy, much larger than the visible galaxy itself. When you take a single point in a filament of the cosmic web and start following the flow of matter converging on it, you are seeing in miniature the same process that operates throughout the universe. Dark matter establishes a gravitational well. Gas falls into this well, heats up, cools fragments, and forms stars. Stars group into galaxies. Galaxies orbit around the nodes of the filaments, and each of these galaxies has within itself a version of the same process, where gas clouds fall into smaller gravitational wells and form new stellar systems. Nature repeats the same mechanism on successively smaller scales, like a fractal emerging from a single simple rule applied repeatedly. And then the question you can let rest gently as your breathing slows is this: if a single point of higher density in a nearly uniform universe, given enough time and the action of these few simple laws, can grow to become a node of filaments connecting superclusters of galaxies, stretching for hundreds of millions of light years, what happens when this same process repeats at millions of different points simultaneously, each influencing all the others around it, each shaping the space in which the others form, creating a network where every node exists because all the others exist too? When many points of higher density begin to collapse at the same time, each pulling the gas and dark matter around it, each slightly curving the space in its vicinity, what emerges is not a collection of isolated objects, but something none of these points could have produced alone. The network that arises is a collective consequence, a property that belongs to the whole set and not to any of the individual parts. It is as if the universe, by applying the same simple law in millions of places at once, discovered a geometry that was potentially contained in that law from the start, but only became visible when enough actors began to act simultaneously. This process of large-scale organization is what cosmologists call the large-scale structure of the universe, and its discovery was one of the most surprising moments in modern science. For a long time, it was assumed that, when looking at sufficiently large distances, the universe should appear completely uniform, a sort of homogeneous mist of galaxies distributed equally in all directions. This idea had deep, almost intuitive philosophical roots. If there is no special place in the cosmos, then all places should look alike. This notion became known as the cosmological principle, and it is essentially correct on a sufficiently large scale. But what no one had clearly anticipated was the scale at which this homogeneity finally settles in, and how rich and intricate the structure would be before reaching that scale. The first clue that something more complex was happening came from careful galaxy counts. As early as the 20th century, astronomers realized that galaxies were not scattered randomly across the sky. They tended to appear in groups, and these groups seemed to organize into larger clusters. But it was hard to know if this was a real feature of the three-dimensional universe or just a perspective effect. Galaxies in the same direction in the sky, but at completely different distances, appearing as an illusory group. To resolve this ambiguity, distances had to be measured, and to measure distances, recession velocities had to be measured, the so-called redshifts, which indicate how much a galaxy's light was stretched by the very growth of space during its journey to us. Every galaxy moves away from others because the entire universe is expanding, and the speed at which it moves away encodes the distance. More distant galaxies move away faster because there is more space expanding between us and them. Compiling these measurements in sufficient quantity to reveal the three-dimensional structure was a monumental undertaking. One of the most important milestones was the work that emerged in the late 1980s when Margaret Geller and John Huchra, working at the Harvard Smithsonian Center for Astrophysics, completed what became known as the CFA survey. They had spent years measuring the redshifts of thousands of galaxies, and when they plotted these positions on maps representing slices of three-dimensional space, what appeared on the screen was an image none of those present had anticipated. Galaxies were not distributed uniformly. They were not even grouped in a simple, irregular way. They were organized in elongated structures, in arcs, in thin planes, and in large, completely empty regions. The pattern resembled what we now call the cosmic web, and in that room the impression researchers described was that the universe itself had revealed an anatomy. One of the structures that immediately became famous in that dataset was nicknamed the Great Wall, an extraordinarily flat and extensive band of galaxies that crossed a significant portion of the map. Its dimensions made any human intuition about scale simply stop working, and around it, as always happens in the cosmic web, there were vast, practically empty spaces, the so-called voids, where almost nothing existed. The Great Wall was not an anomaly. It was a particularly clear example of something happening everywhere on the map. Cosmic matter had chosen to concentrate on thin surfaces and in filaments, leaving huge volumes of space almost entirely unoccupied. This pattern of filaments, nodes, and voids is not what one would expect from a universe that simply collapsed at random. A random collapse would produce irregular clumps here and there without the geometric elegance of a network. What produces networks is the directional competition of forces that pull matter in different ways depending on the local geometry. To understand why the universe took the shape of a web and not an irregular mist or scattered clumps, one must think about what happens when a gravitational field acts on a cloud of matter that is not perfectly spherical. Most density fluctuations in the early universe were slightly non-spherical. In practice, all of them were. And when a slightly flattened or elongated cloud begins to collapse under its own gravity, it does not collapse equally in all directions. The collapse happens faster along the shortest axis, the axis along which there is less distance to travel and along which the gravitational force is slightly more concentrated. The result is that the cloud first flattens into a sort of pancake, which cosmologists call a sheet or wall, before continuing to collapse. Then, this flattened structure collapses along another axis to form a filament, and finally the filament collapses toward the points of highest density to form the nodes. This sequence of collapses in successive directions was mathematically described by Yakov Zeldovich, a Soviet physicist whose contributions to cosmology were enormous and sometimes underestimated outside the Soviet Union during the Cold War. What Zeldovich realized and formalized in a mathematical approximation that still bears his name is that the gravitational collapse of non-spherical structures naturally produces a hierarchy of shapes, first planes, then filaments, then points. This sequence is not imposed on the universe from the outside. It emerges from the geometry of the initial fluctuations and the directional nature of gravity. The universe, so to speak, folds itself into progressively more concentrated shapes, and the shapes that emerge first on a large scale are precisely the planar and filamentary structures we see in the cosmic web. The nodes, which are the most massive galaxy clusters, are the last to fully form and the places where matter was most efficiently concentrated throughout this entire sequence of collapses. There is something geometrically inevitable about this progression. Given that the initial fluctuations had slightly ellipsoidal shapes, given that gravity is a force that acts in all directions but with intensity dependent on distance, and given enough time, the collapse into sheets, filaments, and nodes is almost the only possibility. The cosmic web is not one of many possible shapes the universe could have taken. It is the nearly necessary consequence of the initial conditions and the laws governing gravitation. This understanding was deeply satisfying to physicists because it transformed an astonishing observation, the existence of the web, into a prediction that could have been made in advance, and which in a sense was made when computer simulations in the 1990s and 2000s reproduced the cosmic web before observational maps confirmed it in such rich detail. Large volume simulations of the universe, such as those part of the project called Millennium, were another moment of collective insight. In these projects, extremely powerful computers track the movement of billions of dark matter particles over cosmic time, applying the laws of gravitation at each step and recording how the particles move and clump. When these simulations are run from initial conditions, reflecting the fluctuations measured in the cosmic microwave background, the final result is a simulated universe that looks remarkably like the real universe. Filaments, nodes, and voids appear in the right positions, with the right densities, with the right statistics of size and separation. The agreement between simulation and observation is one of the most powerful confirmations that we understand, at least in its general outlines, the process by which the cosmic web formed. What the simulations also revealed with great clarity is the hierarchical character of the organization. The first objects to form were the smallest. The first dark matter halos to collapse contained masses on the order of 1 million solar masses, objects we would now call ultra-compact dwarfs. These objects merged into larger structures, which in turn merged into even larger structures in an ascending cascade of mergers that continues to this day. Galaxy clusters are still in the process of forming, still accumulating mass from their surrounding filaments, still ingesting smaller groups that fall toward them along the filamentary streams. The universe has not reached a state of static equilibrium. It continues to organize itself, although at a progressively slower pace as the accelerated expansion of space begins to compete with gravity on increasingly larger scales. This hierarchy of structures, from the smallest to the largest, from the first compact halos to modern superclusters, is what cosmologists call hierarchical structure formation, or the bottom-up model, and it is one of the central components of the standard cosmological model. The idea that larger structures are assembled from smaller building blocks and not fragmented from larger primordial structures was established both by theoretical arguments and by observations showing younger galaxies in more remote epochs of the universe undergoing more frequent mergers, while today's galaxies are generally more mature and consolidated objects. The distribution of voids in the cosmic web is as informative as the distribution of filaments and nodes. Voids are not simply absences, regions where nothing happened. They are regions where gravity acted differently. Instead of concentrating matter, it progressively evacuated it, expelling particles toward the walls and filaments that border the void. This evacuation process is active and continuous. The few galaxies that exist within voids tend to be smaller, bluer, with more gas available for star formation, and in many cases are being gently pushed toward the edges of the void by the differential gravitational pressure of the surrounding structures. Voids are like bubbles, and their walls are the surfaces where the matter that was inside was deposited over billions of years. The geometry of voids reveals something fascinating about the nature of cosmic organization. It is complementary. Filaments and voids are not separate entities. They are the two faces of a single pattern. Where there is a void, there are filaments at its edge. Where there is a filament, there are voids on its sides. The cosmic web is, in this sense, a topologically coherent object where full and empty define each other, where the concentration of matter in one place is inseparable from the rarefaction of matter in another. This complementarity is one of the reasons the cosmic web looks like a single continuous structure rather than a collection of separate objects. When astronomers began mapping the web in progressively larger volumes, it became clear that the structures initially identified were only local samples of a network extending to distances far greater than early surveys could reach. The 2-degree field redshift survey, known by the acronym 2DF, and later the Sloan Digital Sky Survey, offered maps of hundreds of thousands and then millions of galaxies, revealing the web on an unprecedented scale. Entire superclusters, which in previous decades were known only as local concentrations, came to be recognized as nodes of a network whose filaments stretched for hundreds of millions of light years. The discovery of what became known as Laniakea was a particularly revealing moment of this progression of scale. The name, which in Hawaiian means something close to immense heavenly horizon, was given to the supercluster to which our galaxy, the Milky Way, belongs. The work of Brent Tully and his collaborators, published in the second decade of the 21st century, used detailed maps of galaxy peculiar velocities, the deviations from the pure expansion flow, to trace the gravitational drainage basins of the local cosmic web. The results showed that a vast volume of space containing hundreds of thousands of galaxies was in the process of slowly draining toward a high-density region called the Great Attractor, forming a single basin of gravitational attraction. Within this basin, all galaxies tend to move over enormous timescales toward the center. Laniakea is, therefore, not a group of galaxies in the usual sense, but a gravitational watershed, a region of space whose contents share a common dynamic destiny. The watershed metaphor is accurate and illuminating. Just as a watershed is defined by where water flows and where it converges, a cosmic gravitational basin is defined by where matter flows and where it converges. The borders between terrestrial watersheds are ridges and mountain ranges. The borders between cosmic superclusters are low-density regions, the thinnest filaments, and the voids between them, where matter can flow to either side. Laniakea has a border with other superclusters, and this border is dynamic, not a physical line but a surface of equilibrium between zones of gravitational influence. Thinking of the universe in terms of these drainage basins, connected by filaments and separated by voids, is a way of seeing the cosmic web not just as a static structure, like a pattern frozen in a photograph, but as a system of continuous flows. Dark matter, gas, and galaxies are in perpetual motion within this network. They flow from voids toward walls, from walls toward filaments, from filaments toward nodes. This movement is not chaotic. It is organized, channeled by the geometry of the web itself. Filaments are literally the channels along which matter travels on its journey from low to high densities, and this continuous transport is what keeps nodes growing even today, even after billions of years of structure formation. Rotational organization within the web adds another dimension to this picture. When matter falls along a filament toward a node, it rarely falls in a perfectly straight line. The asymmetry of the mass distributions around the filament imposes gentle torques on the unfolding material, giving it angular momentum. This is one of the mechanisms by which galaxies and clusters acquire rotation, not just through the collapse of individual clouds, but through the torque exerted by the asymmetric geometry of the large-scale structures around them. Recent studies of galaxy alignments along filaments have shown that the rotation axis of galaxies tend to be correlated with the orientation of the filaments feeding them, suggesting that the large-scale web imprints its geometry on the rotational properties of the objects it contains. There is a structural memory. Galaxies carry in their rotation a signature of the direction from which the flows that formed them came. This correlation of orientations on scales much larger than individual galaxies is an example of what cosmologists call intrinsic alignment, and its detection has implications both for understanding galaxy formation and for interpreting observations that use the distortion of distant galaxy images to map the distribution of dark matter. If galaxies are systematically aligned with the large-scale structure around them, this must be taken into account when separating the effect of intrinsic orientations from the effect of gravitational lensing caused by matter along the line of sight. The cosmic web, therefore, is not just the object of study. It is also a factor that enters into the very instruments we use to study it. What emerges from all this investigation is a picture of organization without an organizer, order without intention, complexity without planning. The cosmic web is the result of simple rules applied in parallel for billions of years, and it possesses properties that none of its parts could have anticipated or produced in isolation. Filaments exist because nodes exist. Nodes exist because filaments fed them. Voids exist because filaments and walls drained matter from them. Every part of the structure is what it is because all the other parts are what they are. This kind of global interdependence is one of the most profound characteristics of the cosmic web as an emergent phenomenon. And then, contemplating this network of interdependencies, a question naturally arises that hovers over all this ordered magnificence. The web we know, with its robust filaments, its massive nodes, its well-defined voids, with all this structural richness that maps and simulations have revealed, would it be essentially the same if the initial fluctuations were purely gravitational, if ordinary matter were the sole protagonist of this cosmic drama? What could the gravity of visible matter alone have built, given the same time and initial conditions? The answer, which numbers and simulations make very clear, is that the result would be dramatically paler, less structured, less interconnected, a much fainter shadow of the magnificence we observe. Something had to amplify the process, accelerate the growth, provide the framework upon which everything else was built. This amplifier exists everywhere around you right now, but has never been touched by human hands, never been seen directly by any instrument built by science, never emitted a single photon of light that could unequivocally reveal its presence. It permeates every corner of the cosmos with a density that declines as we move away from the great clusters, but never reaches zero anywhere in the known universe. Physicists call this amplifier dark matter, and the name, chosen not for poetry but for pure intellectual honesty, says everything that can be said with certainty about its nature. It is dark because it emits no light, reflects no light, and does not absorb light the way ordinary matter does. It exists in the complete penumbra of all electromagnetic interaction, indifferent to the photons crossing the cosmos in all directions. Dark matter corresponds to approximately 27 parts out of every 100 of the universe's total energy content. Ordinary matter, that which forms stars, planets, nebulae, your body, and all the atoms that make up everything you have ever touched, represents less than 5 parts out of every 100. The rest, about 68 parts, is dark energy, an even more mysterious and completely different phenomenon that we will address another time. The central point here is the disparity between those 5 parts of ordinary matter and these 27 parts of dark matter. For every gram of hydrogen, oxygen, carbon, and iron that exists throughout the cosmos, there are approximately 5.5 grams of something we do not know intimately, something that gravitates but does not shine, that accumulates but does not collide, that shapes but remains moldable only by gravity itself. This disparity is not a numerical curiosity of secondary importance. It is the beating heart of the entire story of cosmic structure. Ordinary matter, before recombination, that decisive moment when the universe became transparent to photons, was deeply coupled to radiation. Free electrons, free protons, and photons formed a single plasma fluid, where any attempt to concentrate mass was soon fought by radiation pressure, by the enormous force of photons pushing outward against any nodule trying to form. It was like trying to build a sand sculpture in the middle of a constant storm. Every time gravity tried to compact the matter a little, photons dispersed it again, creating those acoustic oscillations we mentioned, waves of compression and rarefaction propagating through the primordial plasma. Dark matter, however, did not participate in this game because it does not interact with radiation, because it is completely transparent to photons in the most radical sense possible. It could concentrate freely while the ordinary matter plasma oscillated and resisted. For hundreds of thousands of years, while the universe remained opaque, dark matter was silently excavating increasingly deeper gravitational wells, building an invisible architecture that awaited the right moment. It was the foundation built before the walls were even raised, the skeleton formed before the organs appeared, the architectural blueprint drawn before the ground was prepared. When recombination finally occurred, when electrons bound to protons to form neutral hydrogen and photons were freed to travel the cosmos freely, ordinary matter suddenly found these gravitational wells already deep, already well-defined, already arranged in an intricate network of filaments and nodes. It simply began to fall. The gravity that dark matter had patiently woven all that time began to call ordinary matter with an irresistible force, and the primordial gas began to flow into those regions of higher concentration, following exactly the pattern dark matter had outlined. Without this pre-existing framework, without this gravitational map already sculpted into the tapestry of space, ordinary matter would have taken much longer to structure itself, and the final result would be much more homogeneous, much less rich. To understand the magnitude of this amplifier, consider an analogy. Imagine you need to create a choir of voices in an absolutely chaotic environment, where noises of all kinds compete and overlap. If you simply ask people to sing together without any preparation, the result will be a cacophony. But if before starting someone has already built an amphitheater with perfect acoustics, with walls that direct the sound, with a seating arrangement that facilitates synchronization among the singers, then the same group of people will produce a harmony that would seem impossible in the original environment. Dark matter was the builder of this cosmic amphitheater, working behind the scenes for a time that ordinary matter simply did not have to build its own structures. The amplification mechanism in detail involves what cosmologists call the Jeans instability, named after the British astronomer James Jeans, who described it in the early 20th century. The central idea is that a gas cloud will become unstable and begin to collapse gravitationally when its mass exceeds a certain threshold, called the Jeans mass, which depends on the temperature and density of the gas. Above this threshold, gravity overcomes internal pressure and collapse begins. Below it, pressure keeps the cloud stable. In the primordial universe, ordinary matter had extremely high temperatures, which raises the Jeans mass and makes it very difficult for smaller structures to collapse. Dark matter, on the other hand, does not possess significant thermal pressure in the conventional sense. Its particles, whatever their nature, were moving in a way that allowed collapse into gravitational wells much more easily. It essentially lowered the effective threshold needed for structures to begin forming, allowing concentrations that would be insufficient to collapse in a pure ordinary matter universe to become cradles of real structures. Computer simulations mapping this process are works of art and science at the same time. The Millennium Project, conducted at the Max Planck Institute for Astrophysics in Garching, Germany, used over 10 billion simulated dark matter particles to reproduce the evolution of the universe over 13 billion and 700 million years. The result was a web that corresponds with astonishing precision to what astronomers observe in the real universe, with filaments connecting clusters, with voids expanding, with the same statistical distribution of structures that the SDSS survey and other major sky mappings have revealed. When simulations are run without dark matter, the result is unrecognizable. The simulated universe remains much more homogeneous, much less structured, without the grandeur of robust filaments and massive clusters that characterize the cosmos we inhabit. But all this cosmic grandeur, all this architecture sculpted by forces operating on scales of hundreds of millions of light years, where does it manifest in a way that can be perceived and appreciated? How does the invisible become visible? How does the abstract become concrete? How does the cosmic web leave its mark on objects and phenomena that telescopes can record and the human mind can contemplate? The most immediate and dazzling manifestation is the galaxies themselves. Each galaxy, from majestic spirals like the Milky Way and Andromeda to the massive ellipticals that dominate the centers of large clusters, is a node in the cosmic web, a point where dark matter accumulated enough to attract gas, allows stars to form and create those islands of light that speckle the night sky. But galaxies rarely exist in isolation. They tend to group together, to organize into larger structures that directly reflect the architecture of the underlying dark web. Galaxy groups, collections of a few dozen to a few hundred gravitationally bound galaxies, are the basic building blocks of this organization. The local group to which the Milky Way belongs contains over 50 known members, dominated by the two giant spiral galaxies, the Milky Way itself and the Andromeda Galaxy, with a swarm of smaller companions in tow. This group occupies a region of space about 10 million light-years in diameter and is being gravitationally attracted by larger structures around it, in particular by the Virgo supercluster, a much larger set housing over 1,300 catalogued galaxies. Galaxy clusters are the next level in this hierarchy, bringing together hundreds to thousands of galaxies in regions that can stretch for tens of millions of light-years. The Virgo cluster, the closest to the Milky Way, is about 53 million light-years away and contains at least 1,300 confirmed galaxies, with a total mass equivalent to about a quadrillion solar masses. The Coma cluster, further away, is even richer, with over 1,000 visible galaxies within a diameter of 20 million light-years. It was precisely in this Coma cluster that the Swiss astronomer Fritz Zwicky made the historic observation in 1933 that planted the first seed of the dark matter concept. Zwicky measured the velocities of galaxies in the cluster and realized they were moving too fast to be held together by the cluster's visible mass. If only the mass of the stars and gas that could be seen were responsible for the system's gravity, the cluster should have disintegrated billions of years ago, with individual galaxies escaping into intergalactic space. There was hidden mass somewhere, mass that gravitates but does not shine. Zwicky called it Dunkle Materie, dark matter in German, and for decades he was considered an eccentric for this claim, until the following decades proved he was right in a way that transcended even his own vision. Vera Rubin and Kent Ford in the 1960s and 70s provided the most convincing confirmation by studying the rotation curves of spiral galaxies. If a galaxy were composed only of the visible matter seen in its stars and nebulae, stars in the outer regions, much further from the dense center, should orbit more slowly, exactly as the outer planets of the solar system orbit slower than the inner ones, following the laws of Kepler and Newton. But what Rubin and Ford observed was completely different. Stars in the outer regions of galaxies orbited at the same speed as inner stars, and in many cases even a bit faster. The rotation curves were flat where they should decline. The only consistent explanation was that galaxies were immersed in enormous halos of invisible matter, giant spheres of dark matter extending far beyond the visible regions, providing the extra gravity needed to keep outer stars in their orbits. These dark matter halos are extensive. For the Milky Way, it is estimated that the halo extends about 600,000 light-years from the center, approximately 20 times the diameter of the visible disk of the galaxy with its stars and gas. The mass of the halo is many times greater than the mass of everything we can see directly. The galaxy you observe when you look at the Milky Band crossing the night sky on dark nights is just the illuminated part of a much larger invisible structure. Beyond individual galaxies, the cosmic web manifests in structures even larger than intergalactic filaments. These filaments are the veins of the cosmic web, cords of matter connecting clusters to each other, transporting gas and galaxies along their axis. Some of the most robust known filaments stretch for hundreds of millions of light-years, making them some of the largest coherent structures known in the universe. Within these filaments, hot gas emits X-rays that space telescopes can detect, and galaxies tend to align along their axis, revealing the invisible skeleton of dark matter that sustains them. Voids are the equally important counterpart to filaments and clusters. These regions of very low density, where galaxies are extremely rare and intergalactic gas is even thinner than anywhere else in the cosmos, can stretch for hundreds of millions of light-years. The Boötes void, discovered in the 1980s, is one of the largest known, about 330 million light-years in diameter, and a slightly spherical shape suggesting a single primordial expansion event. Within its seemingly empty immensity, there is only one catalogued galaxy for every 10 times the volume expected in a typical region of the universe. Voids are not simply empty space in the trivial sense. They also possess dark matter, although at much lower densities than filaments and clusters. And recent studies suggest that voids evolve in a way that tests our cosmological theories, gradually expanding as matter migrates to adjacent filaments, draining toward the nodes of the webs where gravitation is most intense. Voids grow while webs fatten, in a continuous dance of mass redistribution that reflects the current state of the accelerating, expanding universe. There is a particularly elegant and visually impactful manifestation of the cosmic web that astronomers call gravitational lensing. When light from distant objects passes through massive concentrations of matter, whether visible or dark, the curvature of spacetime caused by this mass deflects the light rays, distorting and amplifying the image of the distant object in ways that depend on the mass distribution of the intermediate object. For very large mass concentrations, like massive galaxy clusters, this effect can create spectacular luminous arcs, multiple images of the same quasar or background galaxy, or characteristic deformations that astronomers call shear. The bullet cluster, the result of two galaxy clusters colliding, provided one of the most convincing demonstrations of the existence of dark matter through gravitational lensing. When two clusters collide, the hot gas representing most of the visible baryonic mass gets left behind, slowed by electromagnetic interactions, while individual galaxies pass through relatively unhindered. But dark matter, because it does not interact electromagnetically, also passes through without being slowed, following the galaxies. The result is a dramatic spatial separation between where the hot gas is, revealed by X-rays, and where most of the gravitational mass is, revealed by lensing. This separation is an unequivocal signature of matter that interacts gravitationally but not electromagnetically. You might now be invited to perceive these manifestations in a more intimate, more personal way, even if the invitation seems paradoxical, given the immeasurable scale we are discussing. Every star you see in the night sky is a smaller node within a larger node, part of the Milky Way spiral, which is in turn embedded in the local group, which is attracted by the Virgo supercluster, which is part of an even larger structure called Laniakea, a supercluster containing over 100,000 galaxies and stretching for 500 million light-years. When you look up at a starry night and contemplate the sky, you are looking into the cosmic web from within it, like a neuron trying to contemplate the brain of which it is a part. There is a curious analogy that scientists themselves have noted, not just as a poetic metaphor but as an object of quantitative investigation. The spatial distribution of galaxies in large sky surveys, when compared with brain cortex scan images obtained with tomography techniques, reveals remarkable structural similarities. Filaments branching and converging into nodes, voids between connection networks, a hierarchical pattern of organization repeating its characteristics at different scales. Researchers at the University of Bologna published formal studies comparing the two networks with rigorous statistical methods and found that the topological properties of the two systems, the distribution of the number of connections per node, the presence of clusters, the fractal dimension of the networks are surprisingly similar, even though the physical scales and underlying mechanisms are completely different. It is not that the universe thinks naturally, but that the physics of complex systems interacting gravitationally or electrochemically can converge on similar architectures for reasons we do not yet fully understand. This convergence of shapes on such dramatically different scales suggests something profound about the principles governing the self-organization of complex systems in the universe. When long-range forces connect many individual elements with intensity varying with the distance between them, the result always seems to be a sparse network with nodes and filaments and voids, regardless of whether we are talking about neurons or galaxies. The cosmic web is, in this sense, the grandest expression of an organizational principle that seems to be universal. And now, after all that has been revealed, after understanding the invisible amplifier and its dazzling and verifiable manifestations, the picture that emerges is one of magnificent and comprehensive order. The cosmic web looks like a system in stable equilibrium, with its well-defined filaments and its massive nodes, and its well-defined voids, with matter flowing through these channels in predictable patterns, with the dark architecture providing stability and permanence to the visible structure. It seems at first glance that the web has reached a state of maturity, a regime where the processes that shaped it have done their job and the result will persist indefinitely. But this appearance of stability is deceptive in a way that cosmologists recognize increasingly clearly. The cosmic web is not static, it is in constant evolution, even if this evolution is imperceptible on any human timescale. Filaments continue to fatten while voids continue to grow. Clusters continue to attract matter from their immediate surroundings, becoming more massive while the regions around them become sparser. Galaxies within filaments continue to migrate toward the great nodes, a slow but inexorable cosmological flow that will progressively rearrange the distribution of matter, and there is a force working against this aggregating gravitation, a force that was not present in older models and which, when discovered just a few decades ago, turned all of cosmology upside down. This force is gradually increasing its influence over the fate of the cosmic web, and the implications of this process for the ultimate future of the grandest structure we know reveal that the equilibrium we admire is not eternal, not inviolable, not permanent in any comforting way. The web that maps and simulations reveal with such beauty is a structure that exists within a window of time, and this window has a beginning and an end. And what comes next represents a transformation as radical as the one that gave rise to the web in the first place. The force challenging gravity has no poetic name in the common sense. It is called dark energy, and this name is less a description than a confession of ignorance. We call it dark because we do not know what it is. We only know what it does, and what it does is expand space itself, stretch the geometry of the universe in all directions simultaneously, push structures away from each other with a persistence that does not depend on mass, does not depend on temperature, does not depend on anything we can touch or measure directly. It is in the vacuum. It is the vacuum. Every cubic centimeter of empty space carries with it a tiny amount of this expansive pressure, and because the universe has an astronomical amount of empty space, the cumulative effect is immense beyond any human adjective. During the first few billion years after the Big Bang, gravity dominated. The density of matter and radiation was high enough for gravitational attraction to overcome expansion, and it was in this domain that the cosmic web was born. The fluctuations of the primordial plasma grew, dark matter collapsed into halos, filaments formed, nodes thickened, galaxies ignited their fusion engines and filled the universe with light. All this happened under the sign of gravity as the supreme organizing force. Dark energy was there from the beginning, but its influence was smaller, submerged under the enormous weight of the matter and radiation filling the young cosmos. About 5 billion years ago, the balance shifted. Matter continued to dilute as the universe expanded, but dark energy did not dilute. It remained constant per unit of volume. As the volume of the universe grew, the total amount of dark energy grew along with it, while the density of matter fell. At some point in this trajectory, the two forces crossed and expansion stopped decelerating and began to accelerate. This moment of transition was not a dramatic observable event. It did not produce an explosion or a flash. It was simply the instant the cosmological scales tipped to the other side, and since then the universe has been expanding faster and faster, with an acceleration that increases as billions of years pass. The discovery of this acceleration was made through the observation of type Ia supernovae, which act as cosmic standard candles. Because all supernovae of this type explode with approximately the same intrinsic luminosity, astronomers can calculate the distance to them by comparing the apparent brightness with the expected brightness. In the late 1990s, two independent teams were observing supernovae in distant galaxies, hoping to confirm that the universe's expansion was slowing down. Instead, they discovered that distant supernovae were fainter than they should be, which meant they were further away than models predicted, which in turn meant the universe was expanding faster than it had expanded in the past. Expansion was not slowing down, it was accelerating. The two team leaders, Saul Perlmutter, Brian Schmidt, and Adam Rees, shared the Nobel Prize in Physics for this discovery. What this acceleration means for the cosmic web is a story that unfolds on timescales that eclipse everything the human mind can internalize. In the cosmological present, the web still exists, still grows in sophistication on local scales, still sees galaxies migrating toward nodes, still sees mergers happening within clusters. But on larger scales, superclusters are already being pulled away from each other by expanding space. Laniakea, our galactic superhome, is not a gravitationally bound structure. It is dissipating. Its most distant members are already beyond the point of no return, already captured by accelerated expansion, and will never reach the central node toward which they seem to converge. This reveals the first threshold of rupture of the cosmic web, the first point where order gives way to fragmentation. There is a critical distance called the cosmological Hill radius, or simply the binding horizon, beyond which no structure can remain cohesive in the face of expansion. Structures that are entirely within this radius remain gravitationally bound and will continue to evolve together. Structures that extend beyond it will be progressively dismantled, with the outer parts being carried away while the core remains united. The cosmic web, seen from this perspective, is not a single structure in the process of growth. It is a set of islands of cohesion separated by oceans of space that grow endlessly. The moment cosmology recognized this threshold was also the moment the view of the universe as something tending toward a final unity had to be abandoned. Older models dreamed of a big crunch, a final collapse where all the matter in the universe would return to the point of origin in an inverted mirror of the Big Bang. Other models dreamed of a final static state, a universe that reached thermal equilibrium and remained so forever. Dark energy eliminated both these destinies. What it puts in their place is stranger and, in a way, lonelier. But before reaching the end, one must go through the dramatic phenomena that the tension between gravity and expansion produces in the present and near future, because this tension is not just a slow and gradual process. In certain circumstances, it produces events of a violence that defies any earthly analogy. When two galaxy clusters collide, the scale of what happens has no parallel in any other phenomenon telescopes have ever recorded. The bullet cluster, discovered in its post-collision configuration at the beginning of this century, became one of the most studied objects in modern cosmology, because it offers a unique window into the physics of dark matter. Two massive clusters collided at speeds on the order of several thousand kilometers per second, and when they collided, the galaxies and dark matter passed through each other almost without interaction, because galaxies are mostly empty space and dark matter interacts only gravitationally. But the hot gas surrounding each cluster, the intracluster medium, this gas collided head-on and was brutally slowed by the shock. The visible result is a spatial separation between the components. Dark matter and galaxies continued their trajectory and are now beyond the collision point, but the gas was left behind, concentrated in the center, shining in X-rays with a temperature of tens of millions of degrees. By mapping visible light to find galaxies, measuring the gravitational lensing effect to find dark matter, and using X-ray telescopes to find the gas, astronomers managed to produce a three-dimensional map of the cluster's composition, clearly showing that the dominant mass, dark matter, is not where the bright gas is. This was one of the most direct proofs ever obtained that dark matter exists as a separate component from normal baryonic matter. This type of collision is not rare in the cosmic web. The nodes of the web are continuously fed by filaments bringing smaller clusters towards them. The process of hierarchical structure formation, which built the entire architecture of the web from small fluctuations, continues operating today on the scale of clusters. Smaller clusters fall toward larger clusters, orbit around them, eventually merge. Each merger is an event that releases an amount of gravitational energy equivalent to trillions of times the total energy the sun will radiate in its entire life. This energy goes into heating the gas, accelerating particles, generating shock waves that propagate through the intracluster medium. Shock waves from cluster mergers can have dimensions of several megaparsecs and move through the intracluster gas, heating it, compressing it, generating magnetic fields, and accelerating electrons to relativistic speeds. These ultra-fast electrons interact with magnetic fields and emit radio, creating so-called radio relics, structures that stretch for megaparsecs and are the visible traces left by shock waves in cluster collisions. When a radio telescope points at a merging cluster and detects this diffuse radio glow, it is essentially seeing the electromagnetic echo of a cosmic collision that happened hundreds of millions of years ago. Radio halos are related but distinct structures, while radio relics are at the edges of clusters where shock waves arrived. Radio halos are centralized, filling the internal volume of the cluster with diffuse emission. They are also generated by merger turbulence, but by a different mechanism, involving the reheating of already existing relativistic electrons by turbulence propagating through the intracluster gas. The distribution of halos and radio relics in known clusters is today an indirect map of the merger history in the cosmic web. While you rest somewhere hundreds of megaparsecs from here, Two galaxy clusters are completing an approach that began billions of years ago. The gas of one is already touching the gas of the other. A shock wave with the energy of countless supernovae is forming at the interface between the two structures. The space where this happens shines in X-rays with an intensity no human furnace will ever reach, and no one on Earth knows this is happening now because the light from this event has not yet reached us. This lag between the event and the observation is fundamental to understanding how humanity tries to predict and understand the most dramatic phenomena of the cosmic web. We never observe the universe in real time, we observe the past. When we look at a cluster a billion light years away, we see how it was a billion years ago. When we look at the cosmic web in all its extension, we are seeing a mosaic of different epochs, with closer regions showing the recent universe and more distant regions showing the ancient universe. This temporal depth is both a limitation and a tool. The tool works like this. If we observe enough clusters in different states of merger at different distances and therefore in different epochs, we can reconstruct the statistical history of mergers in the cosmic web. We do not see an individual merger from start to finish, but we see many mergers in different stages, and from this distribution we can infer how a typical merger evolves over time. It is like deducing the life cycle of a tree by observing an entire forest at once, with trees in all phases from seed to rotting trunk. Modern cluster surveys through the Sunyaev-Zeldovich effect, where the hot gas of clusters leaves a characteristic mark on the cosmic microwave background by scattering it to higher energies, have allowed the identification of tens of thousands of clusters in large volumes of the universe. Combining these catalogs with redshift measurements to determine distances, cosmologists can map the distribution of clusters in space and time, tracking how the cluster population grew over cosmic history. This growth is sensitive to the underlying cosmology, especially dark energy, because the rate at which massive structures form depends on the balance between gravitation and expansion. This is where the drama becomes quantifiable. The rate of cluster mergers is decreasing, not because the universe has become more ordered, but because accelerated expansion is progressively isolating structures from each other. Clusters that are within a cosmologically bound radius will continue to merge and grow, but new feeding material, new clusters arriving through filaments, will become progressively rarer as the space between nodes expands faster than gravity can pull matter along it. The filaments themselves are being stretched. The density of matter within them is decreasing. Gradually, they will lose their ability to function as cosmic highways. There is a related phenomenon that happens on an intermediate scale and represents one of the most dramatic transformations a node of the web can undergo. When a massive cluster has its merger interrupted for some reason, or when the hot gas that should continue falling toward the center of the gravitational potential is reheated enough to stop, the cluster can enter a phase of thermal mismatch. The gas in the core, which should be radiating energy and cooling, is heated by some mechanism, and cooling is suppressed. For decades, astronomers expected to find in the cores of massive clusters enormous amounts of cold gas falling toward the center, which should happen if the gas cooled freely. They did not find it. Something heats the gas. This something, the answer the data repeatedly pointed to, is the supermassive black holes at the center of the largest galaxies in each cluster. These black holes, when active, fire jets of relativistic plasma that carry enormous amounts of energy into the intracluster medium. The jets will inflate bubbles of high-pressure plasma that rise through the gas like bubbles in a liquid, and when these bubbles rise and dissipate, they deposit energy into the surrounding gas, keeping it hot enough not to collapse. This feedback between the central black hole and the intracluster medium is one of the most important mechanisms in cluster physics, and represents a form of communication between the smallest and the largest, between the densest object physics allows and the most diffuse and extensive structure in the observable universe. X-ray images of clusters with this activity show cavities, holes in the hot gas created by the plasma bubbles, surrounded by bright edges where the gas was compressed. In radio images, these same regions appear filled with emission from relativistic electrons in the jets. The overlay of the two maps tells the complete story, a story of a black hole feeding on the gas falling toward it, converting some of that energy into jets, and those jets heating the more distant gas, reducing the flow of gas reaching the black hole, thus regulating its own feeding in a feedback cycle that keeps the cluster in a dynamic state far from simple equilibrium. What makes this mechanism even more dramatic is that black hole jets in large clusters can have sizes that rival the clusters themselves. There are systems where jets stretch for several megaparsecs, piercing the intracluster gas and depositing energy in volumes comparable to the size of entire galaxy groups. The galaxy Cygnus A, one of the most powerful radio emitters in the sky, has jets that end in shock points called hotspots and that influence the surrounding gas on scales comparable to the distance between the Milky Way and Andromeda. And Cygnus A is not exceptionally powerful among known radio galaxies. The detection of these dynamic structures was possible thanks to the combination of telescopes at very different wavelengths, and each wavelength reveals a different layer of physics. X-rays show the hot gas and its thermodynamic state. Radio shows relativistic electrons and magnetic fields. Visible light shows stars and galaxies. Microwaves, through the Sunyaev-Zeldovich effect, show the integrated pressure of the gas along the line of sight. Each of these maps, when overlaid, reveals connections that no single map could show. The great modern multi-wavelength observatories, from Chandra in space for X-rays to the VLA in New Mexico for radio, from the Hubble Space Telescope for visible to Planck for microwaves, were designed exactly for this complementary observation. Modern computer simulations try to reproduce all these processes simultaneously. The difficulty is enormous because the relevant physics spans scales that differ by 10 or more orders of magnitude. The same universe that needs to solve the orbits of black holes in galactic nuclei also needs to track the distribution of dark matter in superclusters. No existing computer can do this directly. Simulations use subgrid prescriptions, rules that capture the average effect of small-scale processes without resolving them individually. When these simulations successfully reproduce the observed distribution of clusters, the average temperature of the intracluster gas, the X-ray luminosity of the nodes, this is validation not only of the computational model, but of the physical models that animate it. The illustrious TNG simulation, which tracked the formation and evolution of structures in a cube 300 megaparsecs on a side, with resolution sufficient to resolve individual galaxies, was one of the first to include black hole feedback in enough detail to reproduce the observed bimodality in galaxy properties, with young blue galaxies in filaments and old red galaxies in clusters. This result showed that black hole physics is not just a local detail. It changes the color of the universe on a macroscopic scale. These dramatic phenomena, cluster collisions, black hole jets, megaparsec shock waves, radio relics that persist for billions of years after the collision that created them, do not happen in isolation within the cosmic web. Every node undergoing a merger was connected to filaments that guided the merging clusters to their encounter. Every black hole jet heating a cluster's gas alters the conditions for star formation in the galaxies of that node, and those galaxies are part of filaments connecting that node to other nodes. The disturbance an event creates propagates, influences, reverberates through the larger structure in ways observations are beginning to reveal and simulations are trying to track. The cosmic web does not exist in silence, it resonates. Every filament guiding matter toward a node, every stream of gas flowing along a wall, every cluster merging with another cluster. All these events are part of a living system that exchanges energy between its layers continuously in cycles lasting billions of years and which, nevertheless, obey principles we can begin to understand. The main energy exchange partner of the cosmic web is not a specific object, it is the gravitational field it generates itself. The distribution of dark matter forming the invisible skeleton of the web creates gravitational potential wells of varying depths, shallower wells in filaments, intermediate depth wells in walls, and wells of extraordinary depth in the great nodes. These wells exist as permanent geographies of space, and everything within the web responds to them the same way a ball responds to the bottom of a bowl. Matter hides information about its past in the form of its position and velocity within this gravitational landscape, and it is this information accumulated over billions of years that gave the web its present shape. When a filament feeds a cluster, the gravitational potential energy of the matter descending the filament toward the node converts into kinetic energy. This matter accelerates. When it reaches the cluster, it collides with the hot gas already there, and this collision converts kinetic energy into heat. The cluster gas gets hotter. A hotter gas emits more X-rays. This conversion process from the gravitational potential energy accumulated in the web's structure to the heat of the intergalactic plasma in the nodes is one of the main heating mechanisms of the universe on a large scale. The web does not just guide matter, it heats it by the simple act of guiding it down into its own potential wells. But there is a second partner, as important as gravity, and operating in the opposite direction. This partner is the feedback from supermassive black holes. While gravity collects, compresses, and heats, black holes disperse, stir, and cool the star formation process by interrupting the supply of cold gas. The cycle between these two partners is one of the most important feedback cycles contemporary astronomy recognizes, and it operates on timescales ranging from tens of millions to hundreds of millions of years. The cycle works like this. A cluster accumulates hot gas in its center over tens of millions of years. This gas, as it cools through X-ray emission, should collapse toward the center and fuel intense star formation. But when the gas begins to fall, it feeds the central black hole of the brightest galaxy in the cluster. This black hole responds by firing jets. The jets inflict mechanical energy on the surrounding gas. The gas is stirred, expanded, reheated. Cooling is interrupted. The black hole, with no more fuel falling toward it, quiets its jets. The gas begins to cool again. The cycle restarts. Observations of clusters like Perseus, Centaurus, and others show that this reheating cycle occurs at intervals of tens of millions of years, with evidence of multiple jet events recorded as concentric cavities in the X-ray gas, like rings in a tree trunk keeping the memory of each past season. What makes this cycle extraordinary from a physics point of view is its precision. The black hole does not heat the gas uniformly. It heats just enough to compensate for cooling. Detailed measurements of clusters like MS-076, where X-ray emission was mapped with arcsecond angular resolution by the Chandra Observatory, show that the mechanical power of the jets corresponds within a factor of 2 or 3 uncertainty margin to the gas energy loss rate through X-ray emission. This balance was not imposed by anyone. It emerged from the system's dynamics over billions of years of evolution, like a thermostat that learned to calibrate itself without instruction. The feedback cycle between gravity, gas cooling, and black hole jets is a system operating on different timescales simultaneously, and understanding its behavior on each of these scales reveals different layers of its nature. In the short term, which in cosmology means decades and centuries, what we observe is practically static. A cluster like Perseus seems frozen in a specific configuration, a central black hole with jets stretching for a few hundred kiloparsecs, cavities in the gas visible in X-rays, a central galaxy forming stars at a modest rate. If we observe this same cluster 100 years from now, it will look practically identical. The cavities will have expanded slightly, the jets will be in a slightly different phase of their cycle, but the general structure will be recognizable. On scales of millions of years, the behavior changes character. What was static reveals itself as pulsating. Jets turn on and off in cycles that can be measured by the position and size of different generations of cavities in the gas. The gas that was reheated in one cycle gradually cools, fueling the next cycle. The central galaxy oscillates between phases of low and high star formation in response to the cooling and reheating of the central gas. High-resolution hydrodynamic simulations modeling these systems over hundreds of millions of years show that the cycle is not perfectly periodic. It has irregularities, bifurcations, episodes where jets fire with unusual power and others where they remain dormant for longer periods than usual. This slightly chaotic character is not an imperfection of the model. It is a real characteristic of the system, reflecting the cycle's sensitivity to the specific conditions of the gas at each moment. On scales of billions of years, the behavior changes character again. What was pulsating reveals itself as evolutionary. The black hole grows because in each cycle it ingests some amount of matter. Over time, a more massive black hole produces more powerful jets at the same accretion rate, meaning the same level of jet activity becomes progressively more efficient at heating the gas. This creates a slow change in the cycle's balance, not abruptly, but as a background trend accumulating over billions of years. Today's universe has central black holes in clusters that are, on average, hundreds of times more massive than black holes in clusters from billions of years ago. And this mass evolution changed the relationship between heating and cooling on a cosmological scale. The cosmic web itself as a structure also evolves on this deep timescale. The filaments that today feed the great clusters exist because the density fluctuations of the early universe, the seeds left by the inflationary period in the first moments after the expansion began, created slightly denser regions that slowly attracted more matter, becoming progressively denser still in a process of gravitational amplification that lasted billions of years. In the first few billion years, the web was less pronounced, filaments were fainter, nodes less concentrated, voids less empty. Over time, gravity sharpened the contrasts, like a photographic developer progressively making shadows darker and lights brighter. The web we see today is the result of nearly 14 billion years of this amplification process. But there is a complication that cosmology of the last 30 years has discovered and still does not fully understand: dark energy. When astronomers measured the universe's expansion rate with enough precision to see its variation over time, they discovered that expansion is accelerating. Something is pushing space away from itself, countering gravity on a cosmological scale. This something was called dark energy, and its nature remains unknown. What it does to the growth of the cosmic web is clear: it interrupts it. In a universe dominated by gravity, filaments would continue to grow, clusters would continue absorbing more matter, nodes would continue becoming denser and more massive. But in a universe where dark energy accelerates expansion, a moment comes when regions not yet gravitationally captured by a structure are pulled away too fast to be reached. The web freezes in its current configuration. The filaments that exist today are, to a large extent, the final filaments. The universe will not form comparable new filaments in the distant future. This means we are living in a privileged moment of cosmic history. The web is still active. There is still matter flowing through filaments. There are still clusters merging, there are still galaxies forming, but this moment will not last forever. In a few tens of billions of years, filaments will become increasingly sparse as the matter still in transit is finally absorbed by nodes or dispersed by accelerated expansion. Today's great clusters will become the gravitationally bound and isolated structures of an increasingly empty and cold future universe. The cosmic web is a structure that has a history and will have an end, not an abrupt end, but a gradual dissolution into increasingly isolated islands of matter. The question of the predictability of this evolution touches on one of the most fundamental limits of science. There are two types of unpredictability that are radically different in their nature. The first type is practical unpredictability, that which arises simply because we do not have enough data or enough computational power to solve all equations with all necessary precision. A simulation like illustrious DNG or Eagle resolves the evolution of a cubic volume of universe with finite precision, using dark matter particles representing millions of solar masses each. If the resolution were higher, the results would be slightly different. Not radically different. The web would still exist, clusters would still form at the nodes, but the specific details of which galaxy formed where and when would be different. This is the unpredictability of scale, which increasing computational power progressively reduces. The second type is deeper. It is the unpredictability arising from sensitivity to initial conditions, the phenomenon physics calls deterministic chaos. Chaotic systems are those where a minimal difference in initial conditions leads to completely different outcomes after enough time. The universe, as a many-body gravitational system, has regions of chaotic behavior. The orbits of nearby objects can be sensitive to initial conditions on timescales of millions of years. A specific galaxy in a specific filament might have its orbit deflected by an object that passed near it billions of years ago, a deflection that was imperceptible at first but amplified over time to determine whether that galaxy will or will not be absorbed by a specific cluster. The limit of predictability is not just a technological limit that scientific progress can overcome. It is a fundamental limit that exists because the universe is a system with enough dynamic complexity that its future states are genuinely indeterminable from the present state beyond certain time horizons. This is not a defeat for science, it is one of its most profound results. Science has discovered not only what can be predicted but also the precise contours of what cannot. Knowing where predictability ends is also a form of knowledge. What remains possible even in the face of these limits is statistical understanding. We cannot predict which specific cluster will merge with which other cluster in exactly how much time, but we can predict with considerable precision what the statistical distribution of cluster masses will be in 10 billion years, what fraction of the universe's volume will be occupied by voids, what the typical scale of filaments will be. These statistical predictions are testable because we can compare universes at different distances and therefore at different epochs and verify if the observed evolution matches the predictions. This comparison has been made for decades, and the standard cosmological model, with cold dark matter and dark energy, reproduces observations with a fidelity that still surprises the very cosmologists who developed it. There is something deeply moving about this point. We beings who exist for a few decades on the surface of a planet that exists for a few billion years in a galaxy that exists for just as many billion years within a web that formed over the entire history of the cosmos, have developed in a few centuries of systematic science the ability to predict, even if statistically, even if with limitations, the large-scale structure of a universe tens of billions of light years across. The scale of this intellectual achievement is itself a cosmic thing. The beauty of the cosmic web is not just in its appearance, although its appearance is extraordinary. It is in the combination of two qualities that rarely appear together: comprehensibility and inexhaustibility. The web is comprehensible because it emerges from simple principles: gravity, initial conditions, the expansion of space. Any physicist with enough knowledge can write the equations governing it in a few pages. And yet, even with these equations in hand, the web continues to produce surprises. New structures simulations had not anticipated, new relationships between properties no theoretical argument had predicted, new scales of organization emerging only when observational data reaches enough precision to reveal them. Every time astronomy looks at the web with a better instrument, a more sensitive radio telescope, a deeper spectroscopic survey, a higher resolution simulation, it finds not the end of complexity, but a new layer of it: shockwaves stretching for megaparsecs, magnetic filaments connecting clusters before their merger, intermediate temperature gas-filling filaments, and which for decades evaded direct detection because it is too hot to emit in the optical band and too cold to emit efficiently in X-rays, what cosmology calls the warm-hot intergalactic medium, which may contain up to half of all the baryonic matter in the universe in a state that is still difficult to observe. Every answer generates new questions. Every open question answered opens a wider horizon of questions not yet formulated. This property, being at the same time deeply comprehensible and inexhaustibly surprising, is perhaps the clearest sign that we are facing something that deserves the name of beautiful. Not beautiful in the superficial sense of pleasing to the eye, although the cosmic web is that too. Beautiful in the most rigorous sense, that in which the mind finds in the contemplated object a correspondence between its own structure and the structure of the world. The cosmic web is comprehensible because the mathematics humans developed to describe the universe reflects something real about how the universe works, and it is surprising because the universe is richer than any theory humans have developed so far. There is an ancient tradition in physics and mathematics of seeking the simple behind the complex, of believing that beneath all the exuberant phenomenology of the world, the diversity of forms, the multiplicity of processes, the richness of emergent behaviors, there is a substrate of elegance unifying what seems separate. This tradition has been repeatedly rewarded. Newtonian mechanics unified the physics of projectiles and the physics of planets. Thermodynamics unified heat and mechanical work. Maxwell's electromagnetic theory unified electricity, magnetism, and light. General relativity unified gravity and the geometry of space-time. In each case, what seemed diverse revealed itself to be different manifestations of something single. The cosmic web, with all its complexity of filaments, nodes, walls, and voids, with all the interactions between dark and baryonic matter, with all the feedback cycles between gravity, cooling, stars, black holes, and jets, with all the timescales ranging from decades to billions of years, this web, with all this richness, emerged from initial conditions that cosmologists describe with a surprisingly small number of parameters: the amplitude of primordial density fluctuations, the ratio of baryonic matter to dark matter, the universe's expansion rate, the dark energy density, a few numbers. It is hard not to feel that these numbers are themselves symptoms of something even simpler, that there is behind all this cosmic architecture a unifying principle we do not yet fully understand, but that the way the web organizes itself might be showing us, in the only way the universe knows how to show things, through its effects, patiently engraved in the distribution of every galaxy, in every filament of light crossing the dark. These few numbers, amplitude, ratio, rate, density, carry within them a responsibility that transcends any concept we can easily formulate. They are not just arbitrary values the universe chose by chance, like someone selecting recipe ingredients without following instructions. They seem to conspire with each other with a precision that challenges the notion of coincidence, and the cosmic web that emerged from them, with all its filaments, nodes, voids, superclusters, and feedback cascades, is the permanent record of this initial conspiracy, inscribed in the geometry of space over billions of years of gravitational evolution. When cosmologists write these parameters in their equations, they are doing something that resembles less a measurement and more a translation. They are trying to capture in mathematical symbols the original language in which the universe decided to speak. Before there was anyone to hear it, the feedback permeating the cosmic web at all its levels is not a secondary detail of the story, but its invisible protagonist. Understanding the web without understanding its feedback cycles is like looking at a river and seeing only the bright surface of the water without noticing the underground currents determining where every drop will end up going. Gravity pulls matter into filaments, and in doing so makes filaments denser, and by making them denser, makes them even more capable of attracting more matter. This is positive feedback, a cycle amplifying what already exists, transforming small differences into large structures over time. Without it, the universe would be a homogeneous and silent mist, without galaxies, without stars, without the slightest possibility that someone could one day contemplate their own existence and ask where they came from. But the universe also developed negative feedbacks, cycles that stabilize and regulate, preventing amplification from destroying what it itself created. Supermassive black holes at the center of galaxies are the most dramatic example of these regulatory feedbacks. When a black hole accretes excess matter, the relativistic jets it emits inject energy into the surrounding gas with a violence that can interrupt the cooling of that gas for hundreds of millions of years. The hot gas cannot condense, cannot form new stars, and the galaxy enters a period of quiescence lasting until the gas cools enough again to feed the black hole once more. It is a cosmic thermostat regulating the star formation rate over timescales dwarfing the existence of any conceivable civilization. And this thermostat in turn depends on the galaxy's position within the web, because galaxies in dense nodes have access to much larger gas reservoirs than galaxies in peripheral filaments, and galaxies in voids have practically no gas at all to feed their black holes and sustain the cycle. There is a compositional dimension of the web that is rarely mentioned but is fundamental to understanding why the universe we inhabit is chemically rich the way it is. The web is not just a gravitational structure, it is, over billions of years, a cosmic-scale chemical processing machine. The hydrogen and helium filling the primordial universe, the only elements forged in Big Bang nucleosynthesis, were chemically simple, capable of forming only the most basic and unstable molecules. For carbon, oxygen, nitrogen, iron, calcium, phosphorus to exist, for the chemistry of life to exist, it was necessary for stars to form life and die, and for their remains to be recycled into new generations of stars. The cosmic web is the context within which this progressive chemical enrichment happened. Filaments concentrated the gas, galaxies within filaments formed stars, stars synthesized heavy elements and dispersed them through winds and supernovae, and the enriched gas mixed with pristine primordial gas, raising the universe's average metallicity generation after generation. This enrichment process was not uniform across the web. The densest regions, nodes, filament intersections, enriched chemically much faster than peripheral regions, because in them star formation was more intense and prolonged. The giant elliptical galaxies living at the centers of the most massive clusters are, in terms of chemical composition, the most enriched structures in the observable universe. Their light is dominated by old metal-rich stars, descendants of generations and generations of stellar cycles completed within high-density environments. Meanwhile, dwarf and irregular galaxies wandering the peripheries of filaments, or in voids have much more primitive chemical compositions, closer to the primordial universe, as if time had flowed differently for them, as if the web had spared them the intense processing that transformed their luckier or less lucky, depending on how you see it, neighbors in the busiest centers. The planet we live on, with all its molecular and biochemical complexity, is a direct product of this enrichment. The carbon atoms in our bodies were forged inside stars that lived and died before the sun was born. The iron in our blood came from supernovae. The calcium in our bones has a stellar history predating any human, any living being, any ocean or continent by billions of years. And all these atoms got here because the cosmic web organized space in a way to create the environments where intense star formation could occur, where chemical recycling cycles could complete, where the solar system could condense from a gas cloud enriched enough for life with all its improbability to have the ingredients it needed. Looking at the web as an integrated system and not as a collection of separate parts, something remarkable begins to emerge. The web is not just the sum of its filaments, nodes, and voids. It is a system where each component influences and is influenced by all others, where information, in the broadest possible sense of the word, the information contained in the distribution of matter and energy, flows continuously from scale to scale. A galaxy cluster at the center of a web node is being fed by filaments converging on it from multiple directions, and the rate at which it grows depends on the density of those filaments, which in turn depends on the global expansion rate of the universe, which in turn depends on the dark energy density. Pull one thread and the whole web moves, imperceptibly but undoubtedly. Change one parameter and the whole structure reconfigures. This is the characteristic behavior of a truly integrated system, of something that is more than the sum of its parts. Emergence, the appearance of complex patterns from simple rules applied many times in many places, is the fundamental creative principle behind everything the web represents. The rules that created the web are, in their essence, extraordinarily simple. Matter attracts matter, and gravity operates without exceptions, without rest, without preference. But when this simple rule is applied to matter distributions containing small irregularities, the quantum fluctuations, that cosmic inflation amplified to macroscopic scales over billions of years, it produces the most complex architecture the universe has ever created. No additional rule is needed. No external instruction was given. The web emerges from gravity and initial conditions with an inevitability that is at the same time astonishing and serene, as if complexity were always latent in the simple parameters, patiently waiting long enough to manifest. This principle of emergence connects the cosmic web to other patterns we recognize in different domains of experience. The way neural networks create consciousness from individual neurons following relatively simple rules. The way markets create complex price fluctuations from individual agents making local decisions. The way flocks of birds create impressive flight patterns without any individual bird planning the complete pattern. In all these cases, the whole is irreducible to the parts, and the emergent pattern possesses properties that no individual part even contains in potential. The cosmic web is the broadest, oldest, and most fundamental version of this emergence phenomenon. The cosmic prototype of all complex systems the universe would later create on smaller scales and with more elaborate materials. Deep down, the cosmic web is simply gravity remembering what came before. Every filament is a memory of where matter was in the early universe. Every node is the accumulation of all gravitational decisions made in the billions of years since the Big Bang. Every void is the record of what was emptied, what was delivered elsewhere, what left and did not return. The web is the universe writing its own autobiography in the distribution of matter, and this autobiography begins with the initial conditions, those few parameters, and extends to the present, with a narrative continuity no event could have interrupted. There are no holes in this story, no lost chapters. Every galaxy existing today carries in its position, in its velocity, in its chemical composition, the entire history of how it got there. The web is the book, and every galaxy is a word, and the complete sentence is the universe saying, with the language of gravity, exactly who it is and how it became so. When the earlier parts of this journey described primordial fluctuations becoming denser under gravity, they were describing the first traces of this autobiography being written. When they described filaments lengthening and voids expanding, they were describing sentences forming. When they described galaxies condensing at nodes and black holes, regulating the rhythm of star formation, they were describing the narrative gaining complexity and depth. And when they described hydrogen bridges connecting clusters separated by distances light takes hundreds of millions of years to cross, they were describing the reach of this story, the way it encompasses everything that exists without exception. The unifying principle cosmologists still seek, that something even simpler behind the cosmological parameters themselves might simply be the universe's tendency to remember itself, to preserve in its present structure the intact record of its past history. The web is not just what the universe became, it is proof that it forgot nothing. There is something deeply comforting about this idea when you let it rest gently in the mind, without haste, without resistance. The universe keeps records. Nothing is completely erased. Every dwarf galaxy destroyed by a larger galaxy left traces in the stellar halo of its conqueror. Every gas that fell down a filament into a node carried its chemical history. Every photon of light traveling for billions of years to reach our telescopes arrived with the fingerprint of everything it encountered along the way engraved in its frequency and polarization. The universe is extraordinarily faithful to what happened, and this fidelity, this cosmic memory inscribed in the web's geometry, is at the same time what makes cosmology possible as a science, and what makes the cosmos profound as an object of contemplation. The web at this moment, while these words rest in the air like light dust, continues moving with the patient slowness of something that has all the time in the world. The filaments are there, stretched between galaxies that will never be neighbors, invisible and silent, full of the tenuous heated gas cosmologists call the warm intergalactic medium. The nodes are there, pulsing with the activity of hundreds of galaxies sharing the same gravitational neighborhood, each spinning around the common center of mass at a speed no perceptible distance seems to reveal. The voids are there, vast and dark, and surprisingly not empty, full of the dark energy pushing them outward, the primordial gas that has not yet found a filament to follow, solitary dwarf galaxies that never knew any other company. While you rest, the web continues weaving gravity by gravity, second by second, with the absolute patience of something that has existed longer than any word can truly mean. The filaments are rivers that never stop flowing. The nodes are cities that never completely sleep. The voids are the silence that gives meaning to everything else. You are safe. The web connecting every galaxy to the rest of the cosmos also connects every atom of your body to the entire universe, because those atoms were forged in stars that lived and died within filaments, that fell to nodes, that shone for billions of years and then delivered their elements to space. You are made of cosmic history. You are made of the memory the web keeps. You are at home in the universe in the most literal and profound way possible. The universe takes care of you, not with an intention we can easily name, but with the absolute constancy of someone who does nothing else, who never paused, who kept the laws of physics intact over billions of years so that the atoms forming you could eventually meet in the right place and time. This constancy is a form of care transcending any word we have to describe it. Everything is in order. The web is where it always was, doing what it always did, weaving space with gravity and time and patience. Galaxies are in their places, filaments are intact, voids are keeping the silence that belongs to them. Nothing is out of place, nothing needs your attention right now. While you rest, the web continues growing imperceptibly at the pace of cosmic expansion, stretching its filaments through space like a sleeping being stretching without waking up. While you rest, photons of light from the most distant galaxies continue traveling through filaments, carrying their messages from billions of years ago to telescopes not yet built. While you rest, some gas in some filament is, at this exact moment, crossing the density threshold necessary to begin condensing, and in hundreds of millions of years, a new star will shine where today there is only tenuous cold darkness. You are part of this. You always were. Every breath you exhale contains molecules that have been in other bodies, in other plants, in other oceans, and before that, in interstellar gas clouds, and before that, inside dead stars, and before that, in primordial filaments that formed when the universe was only a fraction of its current age. You are not just inside the universe. You are a way the universe found to contemplate itself, to feel its own greatness with something resembling wonder. The web is out there, vast and silent. You are in here, small and at peace. And in some inexplicable way, these two things belong to each other. Close your eyes. Feel the weight of the body resting. Let thoughts dissolve like tenuous gas dispersing into a void, without haste, without resistance, just becoming increasingly rare and calm until nothing remains but silence. The filaments of the web are made of silence between galaxies. Your dreams can also be made of silence now. The web wove you patiently over billions of years, and it can wait while you sleep. There is no urgency in the cosmos. There is only the slow, inevitable movement of things toward what they must become. You are safe. The universe takes care of you. Everything is in order. Good night. The universe continues its silent dance, and we rest in its embrace. Thank you for walking with me tonight. Sleep well.